there is a hyperplane separating C and D, I should say strictly separating C and D, if I assume that C is compact and D is closed. Okay, so we will see the proof of this. Again, there are many hyperplane separation depending on what bounds you can put on C and D. We will just do a few. This one is for just getting a feel of it, how the proof looks, and then we will do what we call a Farkas lemma, which is going to be very, very useful for our duality. And again, you will see what changes is the kind of C and D are, what kind of special things we are putting on them, and how that changes the kind of separation we achieve. Okay? So what do you think could be an idea? Now you have these points, you have this nice, probably this is infinite, convex, right? How would you start to construct a hyperplane separating these two bodies? Great, very good. Right? So, C and D, small c and small d, there are, like we knew that with a point there is always a point which is closest. It sounds believable with two convex bodies, with compact and everything, there will be 2 points which are closest to each other. We take the perpendicular bisector. Okay? Sounds good? This is the idea of the proof. Let's prove it. By the way, I had written this theorem, right, that from the point and the compact body, there are 2 closest points. There is a closest point in the compact body. Just for your knowledge, actually there is a strong theorem which says that if you are minimizing a function, a convex function on a compact body, you can always find the optimal. Okay, so now that if I take this set and for any point here there is a closest point, I take this as a function, I optimize over a compact set, I will find 2 points which are closest to each other. So again, this is an idea from this very strong theorem. I am not going to prove it, but I am saying remember this, that the compact body is nice because the optimum exists. Okay, if you are optimizing a convex function over a compact body, you can find the optimum. The distance from the, so the closest point in this closed body. So for any d, I define it to be distance between d comma c, which is the minimum over, and this from the lemma I studied in the beginning, this is a well-defined function. Okay, and then I take the optimal over this compact set, and then things will be fine. Again, I am also not very familiar with these things. These are all major tools in analysis. They are good to know, and good to know where their proofs are. Okay. Now, so given this, now the perpendicular bisector is basically the hyperplane separating them. Very clear, right? But we need a mathematical proof. This is not okay. This picture proof is just one idea, right? So how do we prove this? What is the equation of this hyperplane? Remember, a hyperplane is A transpose X equal to B, right? So what is A, what is B? Very good. Right? Sorry? Okay, so let me make our task slightly simple. I know that this distance is not 0. Why is this distance not 0? Non-intersecting. Let me look at this hyperplane. Okay, or wait, let me see, which one do I want to look at? this one. They are parallel. You don't see it, but they are. Okay. B is correct by definition. C lies on this hyperplane, so that is my B. Okay. So now I want to show that for all D in D, sorry, I shouldn't say D, I should say Z, transpose Z, this is going to be less than or greater than. You can figure out the direction. Greater than equal to, then you move it to perpendicular bisector, and then this will become strict or something. Oh, sorry, this is already strict. Let's see. Okay. One direction. One of the direction will work, right? So sorry. Oh, you just check the sign of C minus D transpose D and C minus D transpose C. Arey, yaar, you make me do painful work.
C minus D dotted with C minus Z minus C, right? It's basically checking the sign of C minus D and Z minus C. And Z minus C and C minus
So this is correct or not correct? Incorrect. Okay. Okay. So now you know how to check this, or just decide which side will D lie. This is positive. This is greater than 0. Right? So C minus D transpose C is greater than C minus D transpose D. Okay? So everything in this side has to lie on the less side. Okay? So yeah. Okay, but again, what is the idea? It is not by picture because we needed so many assumptions, right? So we need convexity. What does it mean? Suppose there is a point here. Why is it a problem? What are we saying? We are saying that no, oh, exactly. So if there is a point of capital C which lies here, then I know that this entire line has to be inside C. And then the perpendicular or whatever, that is going to be a problem. There is this small thing where this distance will become less. That's the idea. So you see it in picture. If you don't see in picture, I can make a better picture. But the idea again is, if there is a point in C, or actually, you know what, I think this picture is nicer because this is parallel or something. So notice from here that if suppose this set was extended and the point came here, that means this entire line is in D. And then this is an issue. Okay, I will formalize it. I will do it mathematically also, so don't worry. Right. So let's say X element of C lies on opposite side of the hyperplane. I think I'm going to switch all the signs. I think I'm going to show this, but you know where these things are going, right? From picture, basically what I want to show is that no point of C can lie here. Okay, and again, the Z. Good. So that means you are understanding everything. Great. So if X is element of C, it lies on the opposite side of hyperplane, on the wrong side, then I am interested in this line. Right? In other words, I am interested in this I want to say that there is a small theta, positive theta, such that this distance is less than the distance between C and D. Let's analyze this distance. What is the distance? D minus help me out here, minus plus or minus? Okay, good. This is what do I know about this? No, I'm talking about this quantity. I said x lies on the opposite side of the hyperplane, right? So that means this is going to be positive. Okay, again you can see the sign from all that. But yeah, basically if x lies on the, okay, let me just do it, right? So what do I know? Transpose Z. So D is in the smaller side, and I said x lies on this side, right? So then C is bigger than x. X is the smaller side. D is smaller than this, so that means, and x lies on the D side. So that means C minus D transpose is C. Right? That means C minus D transpose C minus X is positive. Okay? Now I'm fine. Great. Now this is positive. Why am I excited about that? Exactly. That means this and this quantity, there is some fixed ratio. Right? If I make theta extremely, extremely small, right? This is going as theta square. This is going as theta. So this will become smaller than this. There exists a small theta such that this quantity, such that whole square becomes less than 2 theta. Okay? And if this is not clear to you, go back and read about asymptotics. O notation, theta notation, omega notation. Theta square is small. Theta is big. That's why we like asymptotics. There is a small enough theta such that this quantity will be bigger than this. Okay? That means this distance will become less than d minus c square, which is a contradiction. So I will finish now with few more separations. Okay, by the way, I think this was already said, but if you want to make a strict separation, in this case, your A will be C minus D, and your B would be because you know that C plus D by 2 is the midpoint, right? Okay, so this at C, it's a middle separation. At C plus D by 2, it will become strict. Okay, I don't need to prove it, right? So now, suppose I have a closed convex set C and a point P, which is not in C. What can I say? Weak separation, middle separation, strict separation. This is closed. How many for strict? How many for middle? Okay, and we always know majority is always right. This time it is. There will be a strict separation because this is compact. Right? This is a simple corollary of the previous theorem. Sorry? Oh, because compactness for which one? For D, like in the proof? Oh, because otherwise we cannot find two closest points. Give me two closest points on this, both closed and convex.
So what about something like that, the mirror image of this in the opposite side? We can find two closest points there.
Oh, I am not saying that two closed convex sets cannot have a strict separation. I am saying for all closed convex sets, we need not. A theorem would say that given these conditions, you always have, right? So I am giving you a counter example. In this case, I cannot find the closest point. There is a strict separation here, by the way, but our proof strategy doesn't work. Oh, actually, yeah. Actually, this is not even true, right? Take this. There is no strict separation. But actually, this theorem gives you a nice description of a convex set. A closed convex set is the intersection of all hyperplanes Do you see it? Given a convex body, you take all the hyperplanes, half space. So, okay, so if I want to be correct about the nomenclature, the hyperplane is A transpose X equal to B. This is the half space. This is the other half space. are you trying to divide infinity into two parts and asking me, is it always half? I'm not going to take that bait. No. Dealt with infinity often. Okay. Right? So, do you see this? Why does it follow from this theorem? So, there was this theorem that a point, you can always strictly separate a point and a closed convex set. So, how can you say that a closed convex set is the intersection of all hyperplanes containing it? So, clearly the closed convex set will be contained in the intersection. Suppose the intersection has an extra point. If the intersection has an extra point which is not in the set, I can find another hyperplane and C lies on the other side of it, right? So this is might seem like a very fancy version, but this is a direct corollary of this theorem. Okay. Good. And by the way, yeah, if I'm really interested in using this, then I will only use the supporting hyperplanes, right? I really don't need to have all the hyperplanes. Just the edges, faces ones are the useful ones. Okay, so I think my time is almost up. I just want to give you another, at least the statement of another hyperplane separation, which is going to be very useful for us, for duality, for strong duality. What it does is, you say that you have a point, P let's say, and you have a C, which is a finitely generated cone, convex cone. Okay? So, given a point and a finitely generated convex cone, how does it look like? Finitely generated cone looks like this, right? A point looks like this. Farkas lemma says there is a hyperplane which separates them and passes through the origin. Clear? So, now it says there is a hyperplane, middle strict separation, but passes through origin. Okay? So, now a closed convex cone is a closed body, right? And we actually know by this previous theorem that there is a strict separation. Farkas lemma is another version where we restrict our closed convex body, we get a worse separation, we get only middle strict separation, we do not get the strictest separation, but hyperplane is nice. It is of the form A transpose X less than equal to 0. Okay, so there exists A, now I don't need B, such that A transpose P is less than 0, and for all X element of C, okay, and again this looks believable. Notice a cone would not have been good enough, right? I need convex, right? Because even this is a cone, so this would have been a problem, right? So I need a closed body, convex body, and then I can get this kind of a separation. So Monday, not this. You give a quiz. On Tuesday, we look at this and how it helps us give dual programs. What was the dual program? Great way to give upper bounds on a maximization problem, or great ways to give lower bound on a minimization problem. Okay, thank you.